Good times, my dear students. Welcome to the today's session. One more way of understanding the valence bond. Different theories explains in a different way how covalent bond forms. But the basic idea for the formation of covalent bond is sharing of electrons between the two atoms. Keeping this principle in mind, different scientists and different methods are explaining how a covalent bond is formed. So to some extent, one theory explains, but in some extent it fails to explain the other properties. So we will go further some better method to understand covalent bonding. The more we advance in learning, the more we learn different theories and what is there exactly using the highly sophisticated devices and instruments. We understand what happens at the molecular level, what happens at the microscopic level of the covalent bond. So with this, I welcome once again for the today's session on the molecular orbital theory. And yesterday we learnt some points. Today we will continue where we have stopped. After the fifth point, sixth point is what? The number of molecular orbitals formed is equal to the atomic orbitals mixing. Kindly recall VBT. Same point is mentioned there also. There what we learnt, number of atomic orbitals equal to the number of hybrid orbitals formed. But here what is using the word? Number of molecular orbitals formed. Okay, so small changes. Number of orbitals mixing is equal to number of hybrid orbitals formed according to VBT. So according to MOT, number of molecular orbitals. Okay, so some points are similar between the VBT and the MOT. MOs can be bonding, anti-bonding, and non-bonding. Once the two atomic orbitals overlaps, we get a molecular orbitals. Excuse me. And in this molecular orbital, there are three types. One is bonding molecular orbital BMO. Other one is anti-bonding molecular orbitals ABMO. Then non-bonding molecular orbitals NBMO. Difference is what? First we'll go to the non-bonding. Two atomic orbitals will come close to a certain distance, but the conditions will not favor. Okay, so that means bonding is not favored. They fall under this category. Due to some reason, they come close, but when the certain set of conditions for the laws of chemical combinations are not favored, no bonding take place. So they are called as actually non-bonding molecular orbitals. That means bond is not formed. Again they separate. Anti-bonding. Anti-bonding means two atomic orbitals come close in such a way that electrons of one atomic orbitals are available, whereas the electrons of the other atomic orbital is not available. That means orientation in space, in 3D, in 3 dimension. Okay, so if that is the condition, no, then it will not go for the bonding. It is called as the opposite of bonding, clockwise, anti-clockwise, like that bonding and anti-bonding. So this is also condition for the not forming the bonding. And one more is what? Energy is very high here. But here no question of energy comes here. Why? First of all, they don't go for the bonding. So in the case of non-bonding, no question of energy. But in the case of anti-bonding, energy is so high because electron not available. They want to repel each other. So certainly more repulsions, more energy, and less stable. So this also is not called as a condition for the bonding. Whereas the third one, bonding molecular orbital BMO, where electron of the one, electron of the other, they are available in the same area. They go for the overlap and they go for the sharing. They go for the exchange of electronic transaction. Then bonding favors, so that energy comes out in the form of liberation, and they go to the least energy state and maximum stability. Out of the three, it is only one, that is the bonding BMO favors the covalent bonding. Bonding molecular orbitals are lower in energy than the corresponding anti-bonding. Just now I explained. Each MO is described by a wave function psi, which in turn associated with a set of quantum number. Here he is making use of what? The latest theory known as a quantum mechanical model. Okay, every molecular orbital is explained and described by a wave function of an electron psi. Okay, so here when the two atomic orbitals comes close, okay, I told there are three favor. One is the non-bonding, one is anti-bonding, other one is bonding. So let us not take first non-bonding. Okay, out of the anti-bonding and the bonding, if you want to understand using the wave function, so two atomic orbitals comes with wave nature. Okay, if the waves match, one wave falls on the other wave. This is called as the constructive way of overlapping in terms of the quantum mechanical model. Okay, so it is called as a constructive phase or in phase. Waves are in phase, so they are ready to combine, they are ready to match, they are ready to overlap, they are ready to mix. So that is there. Then they favor the bonding molecular orbital. By chance, if the two waves of two atomic orbitals are not matching, okay, that means out of phase, one wave comes with one direction, other wave comes in a different direction, so it is not a proper orientation. That time overlapping is not effective, so bonding will not happen, they repel, all those high energy will happen, so that means bonding will not take place. So in terms of the wave function, if you want to explain, constructive way of approach or in phase favors the bonding, whereas the destructive way, out phase of wave function, we will go for the anti-bonding. Only these 2 points you keep in the mind, making use of what? Schrodinger's quantum mechanical model. Okay, right. Electrons fill up these orbitals in the same way as atomic orbitals in accordance to the three principles of Bow, Hund and the Pauli. Whatever rule we are following to write the electronic configuration for the atoms, same rules are applied for the writing the electronic configuration for the molecules also. So these three rules are the main important rules, fundamental rules. So these rules are followed by atomic orbital as well as the molecular orbital. Again, every atomic orbital for the combination is has to follow the what? Even quantum number rules also. So these three rules plus quantum number, that means every rule strictly follows for the combination of atomic orbitals, so that molecular orbital is formed according to the MOT. Now let us learn, there are some rules for the LCAO method. What is LCAO? Linear combination of atomic orbitals. L for linear, C for combination, A for atomic, O for orbital. So LCAO means what? Linear combination of atomic orbital, which is a simple method to understand how two atomic orbitals combines. Okay. Always we explain the LCO by taking the simple examples. Okay, and the most simple example is hydrogen with one electron. So once again I will repeat, every method starts with what? Simple explanation. Once we understand the simple explanation, we will go for the complex understanding. Okay, so LCO means what? Linear combination. What is linear? They come in a straight line. They approach in the same axis. So when they approach two atomic orbitals in the same axis with a proper orientation, okay, with a proper energy, then atomic orbital will combine and go for the formation of the covalent bond, and that is known as what? Linear combination of atomic orbitals. And there are certain rules are there, so we discuss one by one. Rule number 1: the same energy of combining orbitals means what? The combining atomic orbitals must be equal energy or approximately same energy. This is already told in the what? Salient features. Same points are repeating again and again under the different headings. Same symmetry along the atomic orbital. If p orbital comes in a proper axis, okay, one more p orbital comes in the same axis, okay. Otherwise, if it comes in a different opposite axis or the direction or the orientation, again there is no possibility of what? Bonding. So atomic orbitals with a proper orientation, proper symmetry, then only approach is good. Proper overlap between the atomic orbitals. The two atomic orbitals will combine to form molecular orbital. Okay. Greater is the extent of overlap. This make it as extent. EXTNT, T, okay. Extent of overlap of atomic orbital, greater will be the nuclear density. The more effective overlap of the two atomic orbitals, then electrons are concentrated between their nuclei. So if the electrons are concentrated under the control of the both nuclei, then that is the best combination, and then it is called molecular orbital formation. Okay, right. Now there are some conditions for the combination. If you want to explain by LCO method, then there are some conditions. Condition number 1: the combining atomic orbitals must have the same or nearly the same energy. See, under the say different heading, one more similar point. The combining atomic orbitals must have the same symmetry about the molecular axis. Okay. The combining atomic orbitals must overlap to the maximum extent. Once again, they repeated. And this is new. What new? This was there already, but in a different way. One molecular orbital out of three molecular orbitals favors bonding. What are those three MOs? Three MOs are bonding, anti-bonding, and non-bonding. Out of the three MOs, it is the bonding molecular orbital, BMO, favors the bonding. Please see, by taking the example of hydrogen, we explain the LCO method by using the quantum mechanical model wave function C. This is the energy, increasing energy. Atomic orbital of one hydrogen, atomic orbital of other hydrogen with opposite spin, they approach. Okay, when they approach, right, if they go for the out phase, destructive way of approaching, anti-bonding. If they go for the constructive way, maximum overlap, correct intermixing, constructive way, in phase, then it is called as the bonding molecular orbital. So plus indicates what? BMO. Minus indicates what? Not favoring the bonding or anti-bonding molecular orbital. Here, first this is formed. Okay, main equation forms. Two orbitals are approaching. So okay, so one is BMO, other one is anti-bonding molecular orbital. Okay, this will not favor. This will favor the bonding. This is the lower energy. This is the higher energy compared to the atomic orbitals which are combining. So this is the energy of the combining atomic orbital up to here. This much energy. Now you compare the energy of the anti-bonding, which is very high, whereas if you compare the energy of the bonding molecular orbital, it is very low. So lower energy favors the maximum stability. So this is favors the molecular orbital, that is sigma. Means what? Sigma means bonding molecular orbital. Sigma star, this is the symbolical way of representing. Sigma star is what? Anti-bonding. Star indicates anti-bonding. Okay, what is sigma here? Sigma refers to the single bond, straight away axial overlap. If it is pi is there, then sideway overlap. Please recall VBT. Okay, sideway overlap, pi bonding molecular orbital. Pi star indicates what? Sideway overlapping but anti-bonding. Okay, right. Graphical way of representing. Okay, this is what they are coming in phase, best phase, constructive way, bonding. Okay, this diagram is shown in the third slide of discussion. Okay, please recall. And this is anti-bonding where waves are not matching. 1 plus here, 1 plus here, they are not matching properly. Node is formed. The electron is not available at all. So this is called anti-bonding. So together, one more way, bonding, anti-bonding. Okay. Thank you, my dear boys. With this, tomorrow we'll discuss the remaining part. Okay. Thank you very much.